Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan and I am a chemical engineer. I have prepared a training course on turbines and motors in refineries and chemical plants, which will be beneficial for those who are working in oil and gas refineries and chemical plants. After completing this course, you will be able to identify the different kinds of turbines, review the history of steam turbines, describe the operating principles and components of a steam turbine, describe the types of steam turbines, list the startup procedures for a steam turbine, identify the basic components of a gas turbine, describe how a gas turbine operates, identify the basic components of an electric motor, describe how an electric motor operates. Before starting the course, let us have a look at key terms. Condensate is moisture produced when steam, hot gases, or vapors condense, that is changed to the liquid state. Exhaust valve is a valve used to block steam turbine outlet steam. Gas turbine is a device that uses high-pressure gases to turn a series of turbine wheels to provide rotational energy to turn an axle or shaft. Governor is speed control device that adjusts the governor valve. Governor valve is an automatic valve that controls steam turbine speed by regulating the amount of steam admitted. Heat soaking is a turbine warm-up procedure designed to remove condensate and warm the internal parts, includes slow rolling the turbine at low speeds between 200 and 500 RPM. Hunting occurs when a steam turbine speed fluctuates while the controller searches for the correct operating speed. Hydraulic turbine is a device that uses high-pressure liquids to turn a turbine wheel attached to a pump generator. Impulse turbine is a steam turbine with a blading design that causes rotation of the blades and shaft when high-velocity steam from an external source pushes on it. Labyrinth seal is a shaft seal designed to stop steam flow in a steam turbine, consists of a series of ridges and intricate paths. Nozzle is a device designed to restrict flow and convert pressure into velocity. Overspeed trip is a safety device used to shut down a steam turbine when it exceeds its rotational speed limit by closing the turbine trip valve. Reactive turbine is a steam turbine with a fixed nozzle and an internal steam source. Sentinel valve is a spring-loaded automatic relief valve that makes a high-pitched noise when turbine speed approaches the design maximum. Slow roll is controlling turbine speed at low, 200 to 500 RPM. Steam chest is area where steam enters a steam turbine. Steam strainer is a mechanical device that removes impurities from steam. Trip valve is a fast-closing steam inlet valve operated by an overspeed trip lever. Wind turbine is commonly referred to as windmill, uses air pressure to pump water, grind grain, and operate small generators. Kinds of turbines. Turbines are classified according to their principle of operation and the type of fluid that turns them. The four main types of turbines are steam, gas, hydraulic, and wind. In steam turbines, impulse movement, the rotor turns in response to the force or velocity of a gas. In hydraulic turbines, reaction movement, the rotor turns in response to the pressure of a liquid. Gas turbines use high-pressure gases, and wind turbines or windmills use air pressure. Steam and gas turbines are the two types most commonly used in industry. Steam turbines are typically classified as condensing, non-condensing, reaction, or impulse. In condensing turbines, exhaust steam flows to surface condensers. Condensing turbines operate at vacuum pressure. In non-condensing turbines, exhaust steam is utilized in low-pressure steam applications. In reaction turbines, steam is discharged from a nozzle mounted on the rotor. Movement is a reactive response to the release of steam from an internal source. In impulse turbines, steam from an external source acts on the rotor to create movement. Most plants use this design. Each of these designs can have one or more stages. This table lists the parameters of turbines. History of steam turbines. In 200 BCE, Archimedes described a device used by ancient Egyptians. This device consisted of a hollow globe, mounted on bearings, with a series of nozzles on the side. Water is poured into the globe and heated to boiling. As the water boils, it is converted to steam and escapes through the nozzles, rotating the globe. The globe rotates because of the effects of the escaping steam. The rotation of the globe demonstrates Newton's third law of motion: for every action there is an opposite and equal reaction. Modern steam turbines operate under the same principle. In 1629, the Italian engineer Giovanni Branca designed the first impulse steam turbine. Impulse movement involves a type of turbine blading design that causes rotation of the blades and shaft when high-velocity steam from an external source pushes on the blades. Branca's innovative design directed high-velocity steam against the blades. The impulse design is used in present-day steam turbines. Technical improvements to the steam turbine design have enhanced efficiency and power. Steam turbines have replaced the once popular steam engine because they weigh less and occupy less space. Steam turbines operate with little or no vibration because they have little, if any, back and forth motion. Turbines are very efficient when run at high speed under a heavy load. Turbine efficiency drops drastically when the equipment is slowed down. Operating principles of steam turbines. The primary operating principle of a turbine is to convert steam energy into mechanical energy that can be used to drive rotating equipment. A steam turbine is a device or driver that converts kinetic energy or steam energy of movement to mechanical energy. Steam turbines have a specially designed rotor that rotates as steam strikes it. This rotation is used to operate a variety of shaft-driven equipment. Turbines are used primarily as drivers for pumps, compressors, ocean vessels, turboelectric locomotives, naval vessels, and electric power generation. As high-pressure steam enters a turbine, it passes through a device called a nozzle. Nozzles restrict the flow and increase the velocity of the steam. The nozzle directs this high-velocity steam against the blades of a paddle wheel, causing it to rotate. As the steam passes through alternate sets of fixed and revolving blades, it constantly expands as it moves along. The rotating paddle wheel is attached to a shaft, and the blading and shaft together make up the rotor. Impulse or reaction movement occurs as the steam strikes the rotor, converting the steam energy into mechanical energy. The amount of steam energy needed to perform useful work depends on the pressure range through which the steam expands. The steam used to operate a steam turbine is produced in a boiler. Boilers produce steam that can enter a turbine at temperatures as high as 538 degrees Celsius or average 1000 to 1050 degrees Fahrenheit and pressures as high as 3500 psi inlet and 200 psi outlet. Steam turbines can also run under a vacuum. High-pressure steam is admitted slowly into a turbine to warm it up and remove condensate that is moisture produced by condensation. Steam turbines are used to drive the electric generators in modern power plants. A multi-stage steam turbine is considered to be one of the world's most powerful engines. Modern turbine technology includes 50 or more stages linked along a horizontal shaft. Each stage consists of a set of moving and stationary blades. The curved blades of each stage are designed so that the spaces between the blades act as nozzles and increase steam velocity. As the steam zigzags between the stationary and moving blades, it begins to expand as much as 1,000 times its original volume. Modern turbine design increases the size of each stage, giving the turbine a conical shape as shown in picture. Impulse and reactive steam turbines operate under similar principles. Impulse turbines have a blading design that causes rotation of the blade and shaft assembly, or rotor, when high-velocity steam pushes on the blades. The kinetic steam source is external. Reactive movement occurs when steam escapes from a fixed nozzle attached to the rotor, propelling the rotor. The kinetic steam source is internal. Both impulse and reaction turbines can be either condensing or non-condensing turbines. Condensing turbines exhaust steam into a heat exchanger called a surface condenser that cools and condenses the steam. The condensate is sent to the boiler, where it is converted back to steam. Condensing type turbines are the most efficient type because they extract the maximum amount of energy from the steam. Non-condensing or extraction type turbines are multi-stage turbines designed to take high-pressure steam, use it in the turbine, and then extract a portion of the steam for other use. As high-pressure, high-velocity steam passes over the turbine wheel, the steam expands. This expansion enables the turbine to divert low-pressure steam to other units. Some multi-stage turbines can induce steam into back stages to increase delivered horsepower. They are called induction-type turbines. Basic components of a steam turbine. The parts of a steam turbine may be thought of as being in 4 groupings: rotor, fixed parts, governing mechanism, and lubrication system as shown in picture. A steam turbine may have miscellaneous other parts for adjustments and safety. Rotor. Steam turbines have a set of rotating blades and a row of fixed half-moon blades. The wheel-shaped rotating blades sandwich the fixed blades. Operators commonly refer to the assembly consisting of the shaft and the rotating blades as the rotor as shown in picture. A visual inspection of the rotor reveals that the rotating blades are firmly attached to the shaft. The rotor is statically and dynamically balanced to ensure smooth operation. Turbine velating uses a progressive cavity-type design to move steam through the rotating and fixed blades. Moving blades are made of durable stainless steel that has been rolled and drawn. The blades are securely fastened by a series of dovetail grooves. The correct spacing is maintained by soft iron packing pieces. The shrouded outer ends of the blades prevent vibration and capture steam in the blade path. During operation, steam enters the inner chamber of the turbine, striking the blades with the full force of the high-velocity steam. The blades rotate in response to the steam pressure. Fixed parts. The principal stationary parts in a steam turbine are the fixed blades, throttle valve, steam tight casing, steam chest, nozzle, and bearings, rings, and seals. Fixed blades. The fixed blades as shown in picture are made of durable stainless steel that has been rolled and drawn. The fixed blades are a half-moon shaped ring located in the lower section of the turbine, sandwiched between the moving blades. When fixed and rotating blades are aligned in the correct position, steam passages are formed across the wheel of the turbine. Casing. The casing is composed of a base and covering made of carbon steel or turbine iron. The base and the covering are designed to form steam-tight joints. Gaskets typically are not needed when reinforced flanges are used. Steam chest. The steam chest houses the governor valve, overspeed trip, and steam strainer, a mechanical device that removes impurities from steam. It is composed of carbon steel or iron and is bolted to the lower casing. Nozzle. The nozzles and nozzle block constitute a precision instrument fabricated from a solid block of high-tensile carbon silicon steel that directs high-velocity steam against the rotor. Nozzle blocks are bolted to the steam chest. The nozzle has overlapping exits that allow the steam jets to converge before being directed against the buckets of the rotor. Bearings. Bearings as shown in picture provide radial and axial support for the shaft of a steam turbine. Radial bearings, also called journal bearings, are designed to keep the rotor of a steam turbine from moving from side to side or up and down. Oil supply passages are built into the radial housing, or a slinger ring lubricates the bearings. As the shaft rotates, the lubrication forms a thin film between the shaft and the bearing that allows the system to float. This type of bearing typically is located beside the thrust bearing on one end of the turbine and by the shaft seal on the other. Thrust or axial bearings are designed to control axial, or back and forth, movement along the shaft and to hold the rotor in correct alignment with stationary parts. Thrust bearings are located outside the steam chest next to the shaft seals. During operation, the thrust bearing draws oil up under the rounded edges of the pivot shoes. As hydraulic pressure builds, the shoes tip slightly, allowing more oil to be drawn under the collar. At normal speed, the shoes have a slight tilt, which is sufficient to accommodate an oil wedge. This oil wedge separates the shoes from the collar. Seals. Carbon ring and labyrinth shaft seals are located at the end of each casing along the rotor. These devices are used to minimize the outward leakage of steam under pressure and the inward leakage of air. Carbon rings prevent leakage between the rotor shaft and the casing. The stainless steel spring-backed ring gland is mounted in a corrosion-resistant sleeve that is kept from rotating by a rod passing through the lower housing section. Labyrinth seals consist of a series of ridges and intricate paths designed to stop flow. Governing mechanism. The governor as shown in picture is designed to automatically regulate the speed of the turbine. A shaft-type governor is located internally and mounted to the shaft. Centrifugal force causes the weights to rotate. The weights are constrained by a spring. As centrifugal force increases, the weights move farther from the central shaft, compressing the spring. The rotating spindle is attached to a fixed sleeve, which controls a fulcrum lever. The lever is used to position the governor valve. The governor valve is a corrosion-resistant valve used to regulate steam flow into a steam turbine. An inlet block valve, the throttle valve, outside the steam chest lets steam enter the turbine steam chest. The governor valve is located inside the steam chest. The governor valve controls the amount of steam flow to the nozzle and is a critical part of the overall turbine control system. Multistage turbines have multiple governor valves arranged in a rack. There are two types of governors: electronic, hydraulic speed control, and mechanical, hydraulic speed control. A typical governing system may be divided into three parts: a speed-sensitive element, a motion sensor amplifier to the control valve, and a control valve. Lubrication system. The lubricating oil has 5 functions. It lubricates bearings and gears. It cools the lubricated parts. It transfers frictional heat. It acts as the hydraulic medium for the governor. It acts as the hydraulic medium for the actuation of the governor valves and safety devices. Other parts. Steam turbines have a hand speed changer capable of making 10% speed range adjustments. A sentinel valve, a spring-loaded automatic relief valve, makes a high-pitched noise when turbine speed approaches the design maximum. An overspeed trip is a safety device used to shut down the turbine when it exceeds 115% rotational design limits. A weighted spring attached to the governor hub is used to close the governor and stop valves. An exhaust valve blocks turbine outlet steam. This valve must never be closed when the steam inlet valve is open because the turbine casing could become overpressurized. A butterfly trip valve, which is a heavy-duty valve, is attached to the steam chest. It works independently or in conjunction with the governor mechanism. It is held in place by a powerful trip linkage. Steam turbine problems. Steam turbines are susceptible to 2 types of problem: vibration and hunting. Vibration sensing equipment is used to monitor turbine performance. Probes are used by process technicians to check inboard and outboard radial and thrust bearings. Excessive vibration could indicate failing bearings or internal problems. There are 2 types of vibration: radial vibration and axial movement. Radial vibration increases when the turbine surges or after a cold start when the machinery passes through critical speed. Surging also can affect axial movement in the rotor. Higher bearing temperatures will accompany any of these problems. Operators should be aware that axial movement is the most important consideration when monitoring and troubleshooting vibration problems. Steam turbines are designed to be operated at a controlled speed. If the steam turbine is operated above or below the normal operating set point, a problem known as hunting may occur. Hunting takes place when a turbine speed fluctuates while the controller searches for the correct operating speed. Another problem that causes the steam turbine to speed up and slow down is mechanical linkage binding. As discussed earlier, the governor system is responsible for the speed the turbine operates. Occasionally, the mechanical linkage between the governor and governor valve will bind. This binding causes the steam turbine to hunt. Sticking or binding problems can be resolved by lubricating the linkage on the steam turbine. Inlet steam pressure problems can also cause a steam turbine to hunt. The chemical processing industry attempts to maintain constant pressures on utility steam heads. Occasionally, boilers go down, or larger demands are made on the system. A fluctuation in the suction steam pressure affects the turbine. On hot days, the system may work perfectly, but cold weather might create problems for your turbine. Some steam turbines are equipped with hand valves that can be opened to admit more steam into the system or closed to reduce flow. Hand valves typically are opened during high load operation and closed during low load operation. Start up a steam turbine. To start up a steam turbine, follow the operating procedure as follows. 1. Visually inspect turbine for damage. Reset overspeed trip. Check lube oil level for turbine governor. Ensure that rotating equipment covers are in place. If turbine is damaged, contact machinists for closer inspection. 2. Drain condensate from turbine. Slowly backfeed low-pressure steam into turbine exhaust. This will slowly heat up the turbine and minimize thermal shock. 3. Check lubrication system's constant level oiler. Check cooling system. Check seal system where the shaft enters the casing. Cooling water circulates through the bearing jackets continuously. 4. Slowly open the throttle valve and bring the turbine speed up 10% to 20% normal operating speed. This step is called heat soaking and includes slow rolling, controlling the speed at 200 to 500 RPM. 5. Bring turbine up to operating speed by opening the throttle valve, listening for line-out sound, and checking governor linkage. If you open the throttle valve quickly, the governor will not have time to get control and the turbine may surge above limits. Gas turbines. A gas turbine is a device that uses high-pressure combustion gases to turn a series of turbine wheels to provide rotational energy to turn an axle or a shaft. Gas turbines are used to operate electric generators, ships, and racing cars and are a primary component of jet aircraft engines. There are 3 primary parts of a gas turbine system: an axial compressor, a combustion chamber, and a gas turbine as shown in picture. The gas turbine system mixes compressed air with fuel in a combustion chamber. A spark plug ignites the mixture, which is directed into the suction side of the gas turbine. The hot combustion gases rush into the gas turbine, causing the turbine wheels to turn. Hot exhaust gases are discharged from the body of the gas turbine. The air compressor and the gas turbine are mounted to the same axle, which is connected to the workload. When the air compressor and the combustion chamber are used in combination, the device is frequently referred to as a gas generator. During operation, a fraction of the power generated by the turbine is used to run the compressor. When the air compressor pulls air into the system, the pressure increases. When the compressed air mixes with the fuel and is ignited, the higher pressure allows the mixture to burn better. The fuel used to operate a gas turbine is natural gas or oil. The hot combustion gases produced by the gas or oil are used in the same way a steam turbine uses steam to turn the rotor. The air for combustion is generally filtered through a baghouse arrangement to remove airborne contaminants, which would deposit on turbine components. The basic components of a gas turbine system fall under 4 primary areas: the compressor, combustion chamber, gas turbine, and workload as shown in picture. Each of these areas has a number of critical components, and they all are linked by a common axle. The compressor consists of the compressor rotor assembly, stator blades, rotor blades, compressor case assembly, air inlet filter assembly, bearings and seals, and compressor diffuser assembly. The combustion chamber consists of a fuel injector, combustor housing assembly, gas fuel manifold, bleed air valve, and igniter. The gas turbine consists of a gas producer rotor assembly, power rotor assembly, moving turbine wheels and stationary blades, nozzle case and assembly, turbine exhaust diffuser, and exhaust collector. The workload consists of the driven shaft and the driven device. Each part of the gas turbine system is an integral part of the whole unit. Axial flow compressors have replaced most other compressor designs because of the large volume they can handle. The combustion chamber combines two feed components to produce a continuous, high-pressure flow into the turbine. The gas turbine has a number of stages that increase in size to accommodate the expanding hot gases that jet through the moving turbine wheels and stationary blades. Electric motors. The history of electric motors began in 1820 when a Danish physicist, Hans Christian Ørsted, discovered that a wire generates a magnetic field when an electric current is passed through it. The discovery of the principle of electromagnetism opened up a new scientific field. In 1825, an Englishman, William Sturgeon, wrapped a wire around an iron bar and generated a much stronger magnetic field. As scientists learned about this new discovery, a number of improvements were made to the electromagnet. By 1831, an English chemist named Michael Faraday had discovered that when a conductor is passed through a magnetic field, electric current flows through the conductor. This discovery led to the invention of the electric generator. In 1873, the first commercial DC or direct current motor was demonstrated. A Serbian engineer named Nikola Tesla invented the first AC or alternating current motor in 1888. Electric motors are used to operate pumps, generators, compressors, fans, blowers, and other equipment. Electric motors can be classified as either DC or AC. The operation of both types of electric motor is based on three scientific principles. Electric current creates a magnetic field, unlike magnetic poles attract and like magnetic poles repel each other, and current direction determines the magnetic poles. An electric motor consists of a stationary magnet or stator and a rotating conductor or rotor. A permanent magnetic field is formed by the lines of force between the poles of the stationary magnet as shown in picture. In a DC motor, a conductor or armature is located between the north and south poles of a stationary magnet or field structure as shown in picture. A commutator is used to reverse the direction of current, helping transmit current between the power source and armature. The armature is a cylindrical device attached to a drive shaft that is designed to become an electromagnet when current is passed through it. During operation, the armature rotates through the magnetic fields. At set intervals, the rotation cuts across the magnetic fields, reversing current flow. This process occurs on each half rotation of the armature. The field structure provides a magnetic field for the armature to move through. Magnetic fields are composed of lines of force. In DC motors, the terms field structure, field magnet, and field coils may be used to represent the stationary magnet. When electricity passes through the conductor in a DC motor, the conductor becomes an electromagnet and generates another magnetic field inside the original lines of force. As the twin fields increase in intensity, they strengthen each other and push against the conductor. The current and these strong magnetic fields determine the direction of rotation in a DC motor. The rotor in an AC motor is a slotted iron core as shown in picture. Copper bars are fitted into the slots. Two thick copper rings hold the bars in place. Unlike a DC motor, electric current in an AC motor is not run directly to the rotor. Alternating current flows into the stator, producing a rotating magnetic field. The stator artificially creates an electric current in the rotor, which generates the second magnetic field. When the two fields interact, the rotor turns. A typical AC motor is composed of a stator, field coils, field magnet, rotor, shaft, bearings and seals, conduit box, frame, fan, shroud, and AC power source. There are three basic designs for DC motors: series, shunt, and compound. The difference between designs is due to the circuit arrangement at the field structure and armature. Series motors are connected in series at the armature and the field magnets. Electric current flows through the field magnet and into the armature. Series motors are characterized by their ability to start up quickly. Motor speed is affected by the size of the load. Shunt motors are connected in parallel as current flows through the armature and magnet. Wire wrapped around the field magnet provides the resistance and determines the strength of the current and magnetic field. Shunt motors are characterized by their ability to run at an even speed regardless of load. Compound motors are connected to the armature with two magnets, one in series and the other in parallel. Compound motors have the characteristics of both the series and shunt motors. Turbine and motor symbols. Turbines and motors can be represented by symbols. This picture illustrates steam turbine and motor symbols. Turbines convert kinetic energy or energy of movement to mechanical energy that is used to impart rotation to shaft-driven equipment. Turbines can use the kinetic energy of liquid in hydraulic turbines, wind in windmills, steam, or gas. As steam enters a steam turbine, it is directed into a nozzle. The nozzle directs the steam onto the belading, which is attached to the shaft. The belading and shaft make up the rotor. Movement occurs as the steam strikes the rotor, converting the steam energy into mechanical energy. Steam turbines typically are classified into the following categories: condensing, in which exhaust steam is condensed, non-condensing, in which exhaust steam is used in low-pressure steam applications, reaction, in which steam is discharged from a nozzle mounted on the rotor, and movement is a reactive response to the release of steam, impulse, in which steam acts upon the rotor to create movement, single stage, and multistage. Most plants use the impulse design. A gas turbine uses high-pressure combustion to turn a series of turbine wheels to provide rotational energy to a driven device in the same way a steam turbine uses steam to turn the rotor. The gas turbine system mixes compressed air with fuel in a combustion chamber. A spark plug ignites the mixture, which is directed into the suction side of the gas turbine. The hot combustion gases rush into the gas turbine, causing the turbine wheels to turn. Electric motors are used to operate pumps, generators, compressors, fans, blowers, and other equipment. The operation of an electric motor is based upon three scientific principles. Electric current creates a magnetic field, magnetic poles attract and repel each other, and current direction determines the magnetic poles. An electric motor consists of a stationary magnet or stator and a moving conductor or rotor. A permanent magnetic field is formed by the lines of force between the poles of the magnet. That's all, gentlemen. If you like my training course, please follow my YouTube channel Petro Intelligence for more courses. Good day and good luck.